All right, in this example, we want to talk about a really important concept that is involved with working with lines, and that is the slope of the line. In this example, we are asked to just find the slope of this line. And so we're given a picture of the line as well as 2 points the line goes through. So how do we find the slope given this information? Well, first we have to remember what the slope represents for a line. So let's go ahead and write some notes down about that. So when we work with linear equations, a special symbol is used to represent the slope, and that is the letter m. So it's very common to see m represent the slope of a line. And so what does the slope of the line represent? Well, it's the ratio of the change in y to the change in x as we move from one point to another point on our line. So let me go ahead and write that down in a couple different ways. In the numerator of our formula that's going to help us calculate the slope, that numerator can be interpreted or represent the change in y values as we move from one point to another point, and the denominator will represent the change in x values as we move from one point to another point, and we're moving between the same 2 points when we're talking about the numerator and the denominator. In order to find this ratio of the change in y to the change in x, or the slope of the line, we do need at least 2 points that our line goes through, and we have that here. And so now we can actually visualize these two kind of components or pieces of our slope formula. So how can we visualize in the graph that we have pictured here what the change in y is represented by? Well, the change in y values is like a vertical difference between our 2 points, and it doesn't really matter where we do it. Let's go ahead and start with this point right here. If we draw this vertical line going down to right about there, then the length of this vertical line is representing the change in y values as we move from our first point to our second point. And similarly, if we want to kind of visualize or have a picture representation of our denominator, the change in x values, well, going from one x value to another x value, that's a horizontal movement. So we can visualize this change in x values as this horizontal line segment that starts at one of our points and goes to the x value represented by our other point. And what's really nice when we do this process is we get to introduce and visualize a nice right triangle into this problem. And through this right triangle, we can kind of find out more about this slope formula and write it down in maybe a more useful way. So how do we find this vertical height that represents the change in y values? Well, we know this top y value is +1, and this bottom y value down here is -3. And so the question can be rewritten as, or reinterpreted as, is how far apart are -3 and +1, or how far apart are 1 and -3? If we want to find the distance between two numbers, one way to do that is by taking the difference of the two numbers and then technically taking the absolute value if it's negative. But we can find this vertical distance between these 2 points by finding the difference between these two y coordinates. So that'll be like 1 minus -3, and that simplifies to +4. So how do we go from this first point at -4, -3 to the second point, or at least to the y value of the second point? We have to go 4 steps up in the y direction. And so now this other side length of this right triangle that we are introducing, which represents the change in x values, will tell us how far we have to move horizontally from this first point to get to our second point. And well, so that comes down to, again, what is the difference between +4, that first x value, and -4, that second x value. And well, 4 minus -4 is +8. And so now we can see in this example, the ratio of our change in y to our change in x is 4 to 8. Or we could reduce that down to 1/2 just by canceling a common factor of 4. And so if we know 2 points on our line, we can always find the slope. We just got to calculate this ratio that is the change in y and the change in x. Now let's go ahead and write down maybe a more useful formula that we can use to find this ratio. So we were given these x and y coordinates of -4, -3, and 4, 1. So we're going to go ahead and relabel these points with a more general labeling, like we didn't actually know the x and y values are -4, -3, and 4, 1. So in more general, we can represent that first point using something like x1, y1. And the second point we can go ahead and call x2, y2. And so now we can write how we found these change in y and these change in x values in terms of these general coordinates x1, y1, and x2, y2. And just as a note, it doesn't really matter the order in which we label these points. What I mean by that is if we call this one x2, y2, and this point x1, y1, all of our work over here is actually going to be exactly the same once all the dust clears and we simplify. Okay, so now how do we find the change in y in terms of y2 and y1? Well, looking back with our actual values, we took the difference between our y coordinates, so we did 1 minus -3. In general, we can write that change in y as y2 minus y1. So y2 minus y1 represents the difference or the change in y values as we move from one point to another point. And in the denominator, we need to have a similar representation for the change in x values. So the difference between our x values was this x value minus that x value. That's how we got 4 minus -4, which simplified to 8. But in general, we can write that as our first x value of x2 minus our other x value of x1. So x2 minus x1 is representing our change in x in our slope formula. And so I was mentioning earlier that if we relabeled our points, we get kind of a similar or equivalent statement. What I mean by that and how we can write that symbolically is if we change the order of this difference here, we can also write this as y1 minus y2 over x1 minus x2. This is equivalent to just multiplying both our numerator and our denominator by -1 and then distributing that factor of -1. But if we multiply by -1 over -1, that's really just multiplying by +1, which is not going to change the value of the expression or what the expression represents. So we can always calculate our slope using the slope formula. And another common thing you will see in the slope formula, really just as a mechanism to help us remember the slope formula, is it also will be written pretty often as delta y over delta x. Delta is a Greek letter, and it's often used to represent change in math and science. So this is like the change in y values divided by the change in x values. Well, that's the ratio of the change of y over the change of x, and that is the slope of our line. So we did write our answer up here. We found the slope of our line to be 4 over 8 or 1 over 2. Let's make it a little bit more clear by putting it down here and boxing it. And so the slope of our line is 1 to 2. That means every time we change y by 1, the corresponding change in x has to be by 2. Or another way to phrase that is if we want to move up 1 unit in the y direction, it comes at a cost of also moving 2 units to the right in the x direction. So I've said it a few times already that the slope can represent the change from one point to another point. And that's true for kind of any points that are on our line. Although when we calculated the slope in this example, we use these two very particular points. I want to draw a little bit more onto our picture to really kind of drive home and emphasize when we look at that ratio of the change in y to the change in x for any other pair of points, we will get the exact same thing. So some other important points that we often look at when working with lines are the x-intercept. So that's where our line crosses the x-axis, as well as the y-intercept. And that is where our line would cross the y-axis. And so I've just kind of drawn on a couple more points for our line. But with these points, we can draw a lot more right triangles. So don't forget this original right triangle we drew kind of in green here. We found the slope of the line by thinking about the ratio of the height of this triangle to the base of that triangle. The height represents our change in y, and the base represents our change in x. But now let's create a similar triangle between this point and this point. So our x-intercept right triangle right there would look something like this. But then we have to also remember one of those really important facts from geometry about similar triangles. Triangles are going to be similar if all three of their interior angles are measured to be the same. And what's nice about similar triangles is the ratio of their corresponding side lengths is always the same. But what is the slope? Well, we can see in our picture over here, the slope is nothing more than a ratio of 2 side lengths in a right triangle. So we originally found our slope using the ratio from this big right triangle. But if we actually knew the coordinates of this point down here, our x-intercept, then we could find the numerical value of the change in y for this right triangle here and the change in x. And if we took that ratio, we would get the same ratio as we did for our larger triangle. We know that's going to be the case because we know from geometry that similar triangles or similar figures are going to have the same ratio for corresponding side lengths. So this little blue right triangle is similar and has the same ratio of side lengths as our large green right triangle. We could also draw in a right triangle here using these 2 points, that x1, y point that we were initially working with, as well as the y-intercept. But we can see that all these angles are the same in all these 3 triangles that we can now visualize. So the ratios of their side lengths are going to be the same. So the ratio of the height to the width, or the change in y to the change in x, is also going to be the same. Probably driven that home enough now, but let's just draw in one more right triangle using the x and y intercept. So now we see this tiny little blue triangle here. That's proportional or similar to this slightly larger blue right triangle here, as well as this right triangle there, and the larger right triangle that we started with. So it really doesn't matter which pair of points we use to calculate that ratio of the change in y and the change in x. Any pair of points will give us the exact same ratio, and that's really, really helpful when working with lines. We really need to know how to calculate the slope of a line, because it's going to be really important and help us build up the equation of a line, which is what we want to look at next.